First of all, I'd like to join other speakers to thank the organizer and the advisory board for inviting me to share our research on studying PIEZO channels. So from my talk, I hope I could give you the take-home message that we really rely on this characteristic three-bladed propeller-like structure and the remarkable the deformability of piezo channels to sense the force, and that allows us to do lots of important biophysiological functions. As you know, that piezo channels are bona fide mechanical receptors that have been identified by Dr. Adam Patapoutian's lab in the year of 2010 for mediating mechanically evoked catalytic current in mammalian cells. After the identification of PIEZO 1 and PIEZO 2, Adam's lab, and together with other research labs in the field, have really demonstrated that PIEZO 2 plays a critical role in the sensing of touch, proprioception, and also internal reception of our breath, blood pressure change, also fullness of bladder, and also under disease condition like inflammatory condition, it can mediate the tactile pain. And on the other hand, the PIEZO 1 is more broadly expressed in non-neuronal cell types, such as in the cardiovascular system, in red blood cells, endothelial cells, cardiomyocytes, and also in our bone system, in the osteoblast for sensing our own body weight. And also recently we have found that even in the brain, which we normally consider as probably is not a brain organ to receive external force, but we have found that PIEZO 1 in the ultrasound can play a major role in sensing local mechanical environment and control the brain size and cognitive function. So on the other hand, how PIEZO can function at the molecular level to sense force and to mediate all those kind of important cellular function and physiological functions. So to answer these questions, we have determined using cryo-EM to determine the structure of both PIEZO 1 and PIEZO 2, either in detergent or in liposome vesicle in the lipid environment. Based on these structure studies, actually, now we lead into this kind of proposed hypothesis that the curved form of PIEZO channels is kind of in a closed state when this curved state can respond to change in membrane tension and convert to a flattened and open state to allow ions permeate through the channel. And so this is kind of the basic idea of I think it summarized the whole field in the past 10 years of studies. So actually Adam have given the talk, his Nobel Prize talk in the title of How Do You Feel? Molecules that sense touch. Indeed, without PIEZO protein, we have the problem. So for some patients, they lost PIEZO 2 expression, so through genetic mutations. So when we assay their touch sensitivity, they have reduced touch sensitivity. Also, they lost their proprioception. That means they could not feel where their hands or their legs are located. So when these people, without vision input, actually they could not work well. Or you ask them to do the simple task, close the eye to tap their nose. They could not do it because they don't have the proprioception. Then the question becomes, how do PIEZO feel force? So fortunately, when I was a postdoc in Adam's lab, my colleague Bertrand Coast identified PIEZO as the essential component for mediating this mechanically evoked current. When we check the PIEZO-encoded protein, actually it's a very distinct protein. First of all, it's very large, over 2,500 amino acid, and also quite distinct from other ion channels we have talked about today. So they have 30 to 40 predicted transmembrane segments, and they do not resemble any non-ion channels. So the question then we want to ask is whether PIEZO protein itself can form ion channels. So I purified PIEZO 1 mouse PIEZO 1 protein and found that it can form oligomers Then we reconstitute the purified protein into artificial bilayer and can mediate single-chain activities, which could be blocked by the non-blocker leucine red. Together with other experimental evidence, we conclude that piezo protein are pore-formed ion channels. Then the question becomes how piezo channels can convert mechanical force into cation permeation. So we learned from physicists in our primary school that force is invisible. However, the force can be manifested as deformation of the receiving subject. So such as when we shaking hand, it causes deformation. And also when we poke the cell at cellular level, you can see the deformation of the cell, which can activate piezo channel to give this inward cation current, which can undergo inactivation. So then a group of students in my own laboratory were trained to learn patch clamp technique to do functional assay of piezo channels. Then in order to understand the structure-function relationship, then we need to get the structure of piezo proteins. Then we actually really take the advantage of cryo-EM. So we collaborate with Xuemin Li, which is a PI in our university. So two of my students, Qianchen Zhao and Li Wang, work out the purification process of piezo proteins. We use DST as the tag. And you can see from the expression, piezo 1 has a relative good expression, but for piezo 2 had very low expression compared to piezo 1. And we also tried different detergents for piezo 1. The detergent C12E10 seems to work well. However, this detergent does not work well for piezo 2. Eventually, we found that GDN works better for piezo 2. Then Henzhou from Xuemin Li's group, working together with these two students, determined both the structure of piezo 1 and piezo 2. So actually, we determined a series of structure for piezo 1. Actually, we got the first structure in 2015. It's our medium resolution. Then we got high resolution of piezo 1 and the high resolution of piezo 2. And we also identify a piezo 1 isoform piezo, we named that piezo 1.1. We also determined the structure. So all these structures were determined in detergent. So in order to understand how piezo function in the membrane, actually last year we reconstituted piezo protein, piezo 1 into liposome vesicles and get two cool configuration. One is this kind of curved shape, another one is this flattened shape. So with this structure, then for this total novel ion channel and the most complicated ion channel, then we can conduct structure-guided functional studies using mutagenesis and electrophysiology. Then we could propose a series of models to try to understand how piezo function at the molecular level. So you can see from here, the first thing we really determined the 38 TM topology, which is organized in modular architecture. So the first 36 TMs are organized into line repetitive functional unit. We term the transmembrane helical unit, THU, which form the peripheral blades. Then the last two TMs together with extracellular cap domain and the intracellular C-terminal domain trimerize to form the central pore domain. And from this structure, we can from the pore size actually has constriction size. So we term this as the transmembrane gate. So these two modules are collected by two domains. One is this nanometer long alpha helix. We term that beam, collect the peripheral blade to the central pore module underneath, just like shown here. The other domain is called anchor domain, which sits right at the waist of the central pore module, providing a stabilization of the central pore. So with this structure, then we combine mutagenesis, electrophysiology. We perform a series of studies. So first thing, we try to identify the exact ion formation pathway. From this, you can see actually there's a vertical central permeation pathway. Ion could permeate through the cap and go through the transmembrane region and then go into the intracellular side. However, through mutagenesis, actually we found that there are penetration side at both the extracellular side and the intracellular side. Now we believe that actually ions permeate through this fenestration side, go through the central pore and then through the intercellular differentiation side. If we take a slice, we can see the central portion is connected to 3 lateral portals. To demonstrate these 3 lateral portals actually function as ion formation pathway, we collect and mutate the line residues lining the lateral portal, then measure to lysine residue, then measure the chloride to sodium permeability. Wild-type PIEZO1 has a low permeability to chloride because it's a cation channel. So, but for this mutant channel, it has 60-fold increase of chloride permeability. Basically, we engineer an anion-selective PIEZO1 mutant channel. So this also demonstrates that this providing evidence that ions go through these lateral portals. But if you check the structure, actually at the outlet of the lateral portal, there's a structure physically block the lateral portal. We term this as a lateral plug. Interestingly, this lateral plug is located at the proximal end of the beam domain. Interesting, this region actually is located in the splice domain, and so the splice domain lacks this lateral plug gate domain. So we determine the structure of this isoform PIEZO 1.1. We can see then this outlet is just open up. So this suggests that probably this lateral plug gate function as a physical gate to block the lateral portal. To support this idea, then because you have 3 lateral portal and 3 lateral plug gates, so they have to simultaneously open because PIEZO1 has a single unit conductor of 30 picosiemens. Then how the 3 lateral plug gate can coordinate gated structure? We found that this 3 lateral plug gate are followed with this large domain, and one of the residue Y1412 form a hydrogen bond with the E2587, which locate a central axis. So then our idea is the 3 separate lateral plug gates are converged into the central axis. Then the 3 blades make sense the force and then converge to the central axis and then redistribute to these 3 lateral plug gates, allowing a simultaneous gating. To test this idea, then we make a mutation to disrupt this interaction. Then we can detect subconduction state, 1 or 2, 3 opening of the lateral portals. The subconduction state is 10 picosiemens, just 1/3 of the usual conduction of wild-type channel. If we did the mutation in the isoform, actually we didn't see these subconductance, but we increased the unitary conductance. Because for the isoform, you don't have the lateral plug gate, so you don't need this coordinate gating. So this really supports that the coordinate gating of the lateral plug gate can latch them onto the central axis. Then we think the flattening of the blade and beam will convert the mechanical force to control the lateral plug gate. So after we determine the flattened structure, when we compare the curved structure and the flattened structure, we can see a 10 nanometer kind of flattening of the peripheral blade. And this can lead to a level-like motion of the beam. So we think this like function at a level. And this level bend around this position, serine 1341. So we actually propose this as a pivot side of this beam. So indeed, when we mutate these 2 mutations, we can greatly reduce the mechanical sensitivity of the mutant channel. So this basic idea is then the flattening of the blade and beam will partially unplug the lateral plug gate to allow the lateral portal open. So then actually from when we check the classification of the flattened structure, we can see that this density corresponding to lateral plug become fragmented, suggesting that some conformation change of this lateral plug gate. So interesting, using high throughput screening, we identified 2 small molecules, Jedi1 and Jedi2, which is hydrophilic, can activate from the axillary side to activate PIEZO1 channel. Interestingly, Jedi, we found the unite the mechanical transduction site, including these 2 extracellular loop and also the pivot position. So the idea is the Jedi bind to somewhere in the peripheral blade. You can use this level-like transduction pathway to allosterically open the central port. So how about the TM gate? Actually, we found that when the piezo become flattened, then the cap domain detach from the blade and it can rotate. We think this motion may control the transmembrane gate. So just like this, you open the rotation convention of the top cap can control this TM gate. So indeed, in the flattened structure, we did see some dilation of the central pore. So mutagenesis, if we delete this whole cap and all these two helix in contact with this blade domain, you can totally abolish mechanical activation of piezo channel. Actually, we have the structure of this mutant channel that still form trimers. So it's not because of their structure is totally disrupted. So based on all this structural function analysis, we can summarize this dual gating system. So piezo channel in the ion permeation pathway has the transmembrane gate, and also in the lateral portal it has the lateral plug gate. We think the flattening of the blade and the beam will cause a lever-like motion to unplug the lateral plug gate, and the motion of the top cap might to open the TM gate. So the intellectual, where the origin of the gating force and energy. So for mechanical gate ion channel, there's two models. One called force from lipid. One of the professors had presented this idea in his talk. That means that the tension itself is sufficient to activate the channel. The other model is called force from filament. That means that the channel needs to interact with extracellular matrix or intracellular skeletons. So people, actually, Ruma Sierra in Adam's lab had used the true droplet barrier system and found that when use this true droplet barrier, when she manipulates the volume of the two droplet, if the two sides is not equal, that means there's a symmetrical barrier. And this condition, when PIEZO1 is incorporated, actually she could record a single channel activity. However, in the symmetrical vesicles, actually low PIEZO1 channel activity could be recorded. This suggests that PIEZO1 is intrinsically mechanosensitive to membrane tension. And they also measured the tension sensitivity, the T50 is 3.4 millinewton per meter. So York's group and also Martinez group also used the PET clamp experiment in cellular setting, also measured the mechanosensitivity by imaging the curvature of the patch and also simultaneously record the channel activity. They can record, they estimate the tension sensitivity is about 1.4 to 5 millinewton per meter. So Rod McKinnon also very interested in the piezo system, how piezo functions. So his lab also determined the PIEZO1 structure in 2017. Given this unique curved shape of a piezo channel, so he kind of proposed this kind of dome model of tension gating. Basically, the basic idea is that piezo protein itself under the membrane can probably form a dome together. So then the tension-induced flattening of this dome will increase the projection in-plane membrane area. So basically like that's shown here. You have this dome, you have the higher curvature, this is the projection area. If you flatten, then you have larger projection area. So in this system, then there are three gating component energy. One is the energy to deform PIEZO1 protein, and the energy to bend the membrane. Also the tension-induced energy change, which equal to tension times of the in-plane membrane area change. So this component will drive the piezo, the dome conformation change. So then in this case, the data A, the in-plane membrane area change, really is the key parameter determine the mechanosensitivity. Because if you have bigger volume of this, then means you need less tension to open the conformation change of a channel. So then actually Rod McKenna and work together with his collaborator. They use atomic force to measure force-induced displacement of PIEZO1 reconstituted in lipid bilayer. In this case, they can estimate the displacement and the force relationship and have a stiffness constant of 7 piconewton per nanometer. And in this case, they detect a 5 nanometer flattening. So in this case, the requirement of 50 BT for 5 nanometer of flattening. So in our case, we decide to use liposome reconstitution to determine the true form of structure. And the idea is to use the curvature mismatch to apply force to hopefully to get the flattened structure. So because of the time issue, I will not go through the technical details. So 4 talented students work together and figure out the condition. Then we can get the very high reconstitution and also the homogeneous sample for structure determination. So in this case, from the 2D classification, we can see these 2 forms. One is the outside-in configuration. The cap is inside the liposome. So that means the curvature has the piezo protein curvature match the liposome curvature. So in this case, the structure is similar to what we have got from the detergent. So the other form actually get this deformed structure. This really is the flattened form. So then we get the 3D configuration of these 2 forms. So with these 2 structures, then we can get the key parameter, how much change of the projected membrane area change. That is 300 nanometer square, and the flatness is about 10 nanometer. Then use the equation obtained by rod mechanics group. Then we can calculate the force. We need 90 piconewton of force to get a 10 nanometer flattening, and about 517 piconewton nanometer of work in order to get the tension sensitivity about 1.9 piconewton per nanometer. This is consistent with the experimental measured value. So actually, one data will show that actually we did one experiment. We tried to see because piezo proteins really have this unique curvature. So actually, we after reconstitute into liposome, we use a soybean liposome, and then we profile the lipid composition. Actually, we found that in the piezo1 liposome actually prefer lipids with spontaneous curvature, but include those planar lipid composition like PC. So really, they can choose those lipids to match its own curvature. So with this, so we have proposed the kind of deformation and curvature gating of piezo channel by gating this thermodynamics and also the physical parameters. We hope to get a precise and quantitative description of the mechanical sensitivity of piezo channels. So after we get this kind of mechanism study, then we can to really understand how piezo can mediate so many different physiological functions. This is the summarize. I just skipped this because of the time issue. So this is the people I have acknowledged during my talk, and also their funding agencies. Last, I will just cite this image to this famous saying, "May the force be with you." Thank you for your attention. Thank you.
Okay, thank you very much. We have time for one question.
Bailong, very good, very nice job. So long blades, so many repeats seem to be excessive that nature created that huge structures. Do they, are they really necessary? Have you tried to shorten the blades and see whether, how much force you need to actually activate it?
Yeah, that's a very great idea. Actually, we tried. We tried to delete some of the THUs, 1 or 2 or 3, but none of those truncated ones, none of those mutant channel works expressed well. So we could not get an answer for that question. Yeah.
During trafficking in the secretory pathway, what is going to happen to the vesicle in which piezo is inserted? I mean, Do you consider this problem? Of
yeah, that's a perfect, that's a great question. Yeah. So basically, this is really kind of unusual, right? Basically, you kind of like curve there. If you have a cell like this, you really kind of curve the cell into the other direction. So how does this happen in the cellular level? We still don't have a clue. Yeah. So probably they can target to some specific like caveolin enriched domains, but we need a lot of more cellular studies. Yeah. Thank you. Okay, thanks.